Hey, Flipped Chemistry, how you doing? We are jumping into our last lecture. Yay! Lecture 32 on nuclear chemistry. This is also our last chapter of the book, and we will finish very, very soon. So, we're talking today about radioactivity, what causes it, what it's useful for, and a little bit of a spoiler. I'm sorry, it does not turn you into a ninja or into a turtle. So, yeah, we're just going to move on from that. Radioactivity is the energy released by certain atomic nuclei. When an atomic nuclei is large, it's unstable. Now, for every number of protons, there is a stable number of neutrons, but oftentimes an element is not on the sweet spot. And so it has to, it falls apart. It breaks down is what it does. And the falling apart happens in something called a radioactive reaction or a thermonuclear reaction. If you're looking at an isotope that is not on the sweet spot of being stable, it doesn't have the right number of neutrons for its number of protons, then it is radioactive, and we call it a radioisotope. Radioisotopes are isotopes of an element that happen to be radioactive. Other isotopes of that element may not be radioactive, but this particular one is. Radioisotopes bond and behave in chemistry just like a regular isotope of that element. C14 is radioactive. C12 is not. You are a mixture of carbon-12 and a small amount of carbon-14. So you are minutely radioactive, and those radioactive carbon-14 molecules don't behave any differently in the carbon chemistry of your body than a carbon-12 does. It's just that every once in a while they're going to fly apart and they're going to turn into something else. So radioactivity is that energy that comes off of a radioisotope. That's the thing. And we have used radioactivity throughout man's history in various different ways. It can be used for clean energy, it can be used for medicine, it can be used for imaging, and of course it can also be used as a pretty amazing weapon. So this is where conversations about dominion are important, and we have these things. Should we be doing everything that we can with them? This is a picture of an alpha particle. An alpha particle is one of three ways that a radioactive element can decompose. One of the things that it can do, if it's too big, it can eject 2 protons and 2 neutrons. And by so doing, it's going to lighten its mass by 4, and it's going to remove 2 protons, so it's going to actually change the element that it is. And when it falls apart in that way and ejects an alpha particle, we call that alpha decay. Alpha particles come zipping out of the nucleus relatively quickly. They're positively charged. They have a charge of 2 because they have 2 protons and no electrons. And they travel fast. They have a lot of mass. They can do damage. If they run into a biological thing, a person or a snail or whatever, they can burn the skin of that organism, but they're not going to go very far down in because they're so big. They don't penetrate very well. They don't tend to go between the spaces of atoms very readily. They tend to whack into the nucleus because they're big. And they also, once they touch something else, they're going to strip 2 electrons off of it because it's basically a helium nucleus that has no electrons. And so it's going to rip 2 electrons off and become a regular old atom of helium. And then it's going to probably find another helium atom that used to be an alpha particle, and they're going to hook up and become He2, and they're happy for the rest of their life. So it doesn't tend to cause a lot of chemistry. It quickly ionizes. It does not penetrate very far. You can stop alpha particles with about a sheet of paper. Okay. The next kind of radiation, alpha. The letter alpha looks sort of like an A, but it's got a swoosh on the top and on the bottom. Like here, swoosh on the top and on the bottom. If you take the Christian fish symbol and just squish it, you kind of get the alpha. So don't write just a normal A, okay? Here is a large unstable nucleus that is becoming more stable by ejecting parts of itself. And so it's kicked out an alpha particle. It is now a different element. It's 4 units lighter and 2 elements lower down on the table, and it's heading towards being stable, okay? This is the kind of particle that was used in the famous experiment that determined the existence of a nuclei in the first place. Because if an alpha particle hits an empty space between atoms, it can go right through, and a lot of them do. But if it comes close to a nucleus, it gets deflected because it's positively charged. And so this detector will pick up alpha particles bombarding it at all kinds of different angles. And of course, if it hits it square on, it comes right back. So this experiment you've seen earlier in chemistry when we were talking about how the nucleus was discovered, and just so you know, they were bombarding gold foil with alpha particles. Okay, a beta particle. Beta looks like a letter B, but it's got a tail. This is actually the lowercase beta. What looks like a big B with a tail. We can also write it as an E because essentially a beta particle is an electron. But it's an electron that comes out of the nucleus, and that's kind of strange because a nucleus doesn't have electrons. A nucleus has protons and has neutrons. So why do electrons come out of the nucleus? Well, what happens is a big unstable nucleus. One of the things that it can do to adjust the ratio of protons to neutrons is the neutron can actually fall apart. The neutron and the proton, we used to say, both have an atomic mass of 1, and they do. The difference between them is so small it's not worth talking about. But just like the mass of an electron is so small it's not worth talking about, the mass of a neutron is actually the same as the mass of a proton plus an electron. And you can take a neutron and you can whack an electron off of it. It's like a chip of a neutron. And that little chip then goes hurtling into space, and it is an electron, but it has come out of the nucleus. So what that does to the atom that just ejected a beta particle is its mass doesn't change because it's still, the difference between neutron and proton is not worth talking about. So its mass is the same, but its ratio is different. It now has one fewer neutron and one more proton. So it's trying to find the sweet spot of the ratio of protons to neutrons, and if the mass isn't going to change, it can change the ratio of proton to neutron by emitting a beta particle. Okay, and it will do that until it gets to some sweet spot of the ratio of protons to neutrons, and it's stable. Okay, so these are negative particles, and they have very, very little mass. Now, we said that a helium nuclei was 4, 2. It had a mass of 4 and 2 protons. This is 0, -1. Why? Well, an electron doesn't have any mass to talk about, so that's 0. And its proton number is -1 because when it left the nucleus of something, that thing's nucleus went up in proton numbers by 1. So it dropped in neutrons, did not change in mass, and the number of protons went up by 1. So what do you subtract from something to make it go up in 1? You subtract -1. So the proton number of a beta particle is -1 and its mass is 0. You can also write it this way to reflect that it is in truth an electron. Okay. Here's just a picture. Here we have sodium 2211. It has a mass of 22. 11 of those things are protons. 11 of them then would be neutrons. Neon 22 is stable. Sodium 22 is not. So we're going to go from 11 to 10, and we're going to eject a beta particle when we do that. Okay. So now gamma rays. Gamma rays are not particles. Gamma rays are energy forms. It's electromagnetic radiation, just like light or radio waves or sound, not sound waves. It's electromagnetic radiation, like radio waves or X-rays or light or ultraviolet or infrared. There's no particle involved, so its numbers are 0, 0. And this may look like a lowercase y, but that's one kind of lazy font's picture of a gamma. This is the gamma. It's a line that swirls under and crosses itself. Okay, so that's a gamma. That's a lowercase g in Greek. And gamma radiation, no particle, no mass, just energy. And so why is a gamma particle emitted? Well, remember when several chapters ago we talked about emission spectra with elements, and we said that electrons can be excited to higher energy states, and when they fall back down, they emit visible light proportional to the change in electron orbits that they dropped back down. So you energize silicon, and it goes up, and then it comes back down, and the energy that it emits is light that is unique to silicon, or light that is unique to chlorine, or light that is unique to sodium. And every element has its own signature of electron emission spectra when electrons are excited and then drop back down. It's a very similar concept in the nuclei, where the nuclei can be excited or go to a ground state. Now, this part is not fully understood. We don't really know enough about the structure of the nucleus to tell you why a nucleus is excited or why it's not excited. or at least I don't understand it. Maybe some brainiac out there does. But the concept applies. You can excite a nucleus by bombarding it with some kind of energy, and the nucleus gets excited. And then when the nucleus drops back down to a ground state, it emits gamma rays. So when electrons drop back down, they emit light. When nuclei drop back down, they emit gamma rays. Okay? And they will go through just about anything. Incredibly high energy and no particle. So there's no physical thing to stop. And it has so much energy, it's just going to keep penetrating. In order to stop a gamma ray, you've got to have lots and lots of material that's very dense. Several feet of concrete, or a sheet of lead that's like a foot or so thick. Okay? So this is the last of the three kinds of particles. So this is just a review. Alpha particles will stop at something like a piece of paper. Beta particles will stop at something like a piece of wood. Gamma rays will need concrete or lead to stop. Okay? We use gamma rays for imaging. We take pictures using X-rays. X-rays are a slightly lesser energetic form of a gamma ray. And then, of course, gamma rays are emitted when we do things like set off nuclear weapons. It's not just the shock wave that comes off of this that kills. It's the burns that keep killing. So gamma radiation will give people cancer years and years later, will cause radiation burns miles and miles away. So this really is the weapon that keeps on killing. We can also use X-rays to look out into outer space, and because gamma rays travel with such high energy, they travel right through a lot of materials that might stop visible light. So if you have a camera that picks up X-ray energy, gamma ray energy, as opposed to picking up light waves, then you get to see things that you can't see on the visible spectrum, because the visible energy, lower energy, gets stopped by like dust clouds and things of that nature. And gamma rays go right through most of that. And so you get sharper, clearer pictures in the gamma ray spectrum than you do in the visible light spectrum. This is just a quick little picture that helps you, again, think about the three kinds of radiation. If you were to have a magnet, a magnetic field here, and you put a radioactive source underneath it and a pinhole, alpha particles will go through the pinhole and will be bent one direction because they're fairly massive, so they've got a lot of inertia, but they also have a charge, so the magnetic field can bend them. Beta particles will bend the opposite direction and harder because they're pretty light, they don't have much inertia, and they're oppositely charged, so they'll bend the opposite direction sharper. And then a gamma radiation will go right through the magnetic wave because it's not ionized, it's not charged, it's just electromagnetic energy. Okay? And unfortunately, no, gamma rays do not turn you into the Hulk either. I know that's the story. Okay, how do you measure radiation? Radioactivity is measured in several ways. I'm going to give you three of them here. There's actually more than that in the book. The one of them that looks at the source of the radiation is called a becquerel. So if you have a radioactive rock and you say how much radiation is coming off of this rock, the more common unit to use would be a becquerel. And the becquerel measures how many particles or gamma rays are emitted per second. So it's a unit of decay per second. And you can use it for alpha, beta, or gamma. That's looking at the substance itself. But medicine doesn't care so much about how strong is that substance. Medicine cares about what am I doing to the tissue when I bombard this person or this whatever in X-rays or cosmic radiation. What's the effect? So if you look at energy added to living tissue, then you're going to be talking about another unit of measurement called a gray. And a gray adds 1 joule of energy, which isn't a whole lot of energy. Adding 1 joule of energy to 1 kilogram of living tissue is a gray. Okay, so the medicine guy doesn't care so much about how strong is the rock. He cares about what did I just do to this person. He uses grays. And then a physicist may want to look at what happens between the target, which may be a person or may be something else, and the source, and says, I know the rock is measured in becquerels, and if this target happens to be a biological system, it's measured in grays. I want to know what's happening to the air in between here. If you look at the ionizing effect on the air, then you're going to be measuring in something called a Röntgen. And a Röntgen is a very large number of coulombs per kilogram of air. Kilogram of air, now air doesn't weigh much, so the kilogram of air is very small, which is why the coulomb has to be very big in order for a Röntgen to be any kind of usable unit. So kilograms of air, how much ionization energy has happened to that air, you measure that in a Röntgen. Okay? Nuclear chemistry, we write nuclear reactions and in a formula called a thermonuclear reaction, and we use shorthand called AZX notation. AZX notation has a number above and to the left of the chemical name, the chemical symbol, and this has to do with the number of nucleons, the number of protons and neutrons, and you've already seen this, right? And then the Z number is the number of protons. We've already actually used this in this lecture, so you're going to see that here the number of protons minus the number of, the mass number minus the number of protons will get you the number of neutrons. Okay, so we can write these equations where we say something like plutonium-208 decomposes through alpha decay, here's an alpha particle, to lead-204. And what's happened is 4 of the items that were used to be in the nucleus are now an alpha particle. And so the new mass of lead is 204. 208 minus 4 is 204. And 2 of the protons that used to make it plutonium left in the alpha particle. So 84 minus 2, now I have lead-82. So the element name has changed and its mass has changed, and this little example shows you how that works. Okay, here's some pictures. This is a nuclear fission reaction where you have some high energy particle, usually a neutron, that whacks into some massive unstable nucleus like uranium-235. And then uranium-235 breaks because of that impact. And it becomes 2 different nuclei. It becomes a nuclei of krypton and a nuclei of barium. And it also ejects more neutrons, which can then go on and whack other uranium-235 elements to keep that going. This causes a chain reaction. That's why once you start a nuclear bond, you can't say just kidding. Because once this has begun, it will propagate itself throughout the sample of uranium, and the explosion just keeps going. Okay? The amount of time it takes for a sample of an isotope to decay into something else is called a half-life. Half the amount of time that it takes for a sample, sorry, saying this wrong. The time that it takes 1/2 of a sample, there you go, to decay into something else is called a half-life. So if you have element A, and element A decays into element B, the time it takes half of element A to decay into element B will be its half-life. And kind of counterintuitive, after 2 half-lives, the whole thing hasn't gone away. It's not linear, it's exponential. So if I have 100 pounds of element A, and after 1 half-life I have 50 pounds of element A, after 2 half-lives I don't have 0 pounds of element A, I have 25, because the 50 got cut in half again. And then after another half-life I don't have 0, the 25 gets cut in half, and I have 12.5 pounds. And then that gets cut again, and I have 6 and 1/4 pounds. And you see how this goes, right? The same unit of time takes half of the stuff and turns it into something else. So every half-life, half of the substance changes. And then different radioisotopes have different half-lives. So let me just give you some pictures for this. 10 pounds of something, after 1 half-life, I've got 5 pounds of it. After 2 half-lives, I have 2.5 pounds of it. After 3 half-lives, I have 1.25 pounds of it. After 4 half-lives, it would be down under, small amounts. So this keeps breaking down. Half-lives are called exponential decay because it's not a straight line. It's an exponential curve. And eventually it gets very close to 0, but in theory it never actually reaches 0, right? In practicality, there would at some point be a last atom that falls apart. Half-lives of different elements, they range in time massively. There are some things that have 4.9 times 10 to the 10th years. Radioactive rubidium, rubidium-87, takes 4.8 and then 9 more zeros in years to turn half of it into something else. Other things are very, very, very short, like 0.0033 seconds. Every 33 10,000th of a second. Half of, I don't even know what FM is, but some radioactive element turns filmorium, maybe, turns into something else. So this half-life is very fast, this half-life is very, very, very small. And so different elements decay different rates, and we can use those to do various sorts of calculations with. So if you have any questions, let me know in the comments field below, or you can see me in class tomorrow, and we will talk all about it. God bless you, Jesus loves you, and so do I.